So the roadblock problem is known to be exponential time complete, which means it's provably harder than any problem in NP, even on a non-deterministic machine. And the proof does not depend on whether P equals NP or not. The proof is certain. Roadblock is harder than any problem in NP. So it's harder than, say, vertex cover. Now, why is that? Why can't non-determinism help us to solve roadblock? Well, it can help us, but it apparently can't help us enough to make this problem solvable in NP. So there's several ways to explain this. And one of the differences between NP and problems that are harder than NP is that in NP, or more concretely in a problem like vertex cover, you're dealing with a static input. You're given one graph, and for that graph, you're trying to solve one question. And that question is, do you have a vertex cover of a certain size? Asking for an optimal strategy in a game like Roadblock is a bit different, because this game is played against a player. So the question kind of is, after player 1 has made a move, what can player 2 do? And player 2, of course, has a number of possible reactions to what player 1 has done. You need to take all of these possibilities into considerations. How player 1 makes the second move or the third move always depends on what player 2 is doing in between. And that is why this problem here is intuitively exponential time complete, because after every move that player 1 makes, you have to consider all of the possibilities that player 2 makes, and there's no way around that. Instead of here where we can just guess a small vertex cover. There's a description for this that is a little bit more formal. You can say that NP is kind of the set of problems that have a short proof, and by short I mean a polynomial time verifiable proof. So, for example, for vertex cover, when I tell you I have a vertex cover that only uses 5 vertices, and you ask me, please show me that vertex cover, well, I can just specify those 5 vertices to you, and you can check yourself that they will make up a vertex cover for the input graph. Now, for a game like Roadblock, that is not that easy, because if you said player 1 can always win this game, and I ask you, I want a proof of that, then we again get into the situation that the proof of the optimal strategy is exponential in size, because that proof will basically start out by saying, okay, this is the first move that player 1 should make, but then there's a couple of reactions that player 2 could have to that move. So let's say it branches out. So this is what player 1 is doing, and this is what player 2 is doing. Now, for each of these reactions of player 2, I would again, in this proof, have to specify what player 1 is supposed to do. But then, as you see, it branches out. Player 2 again has a number of possible reactions that it can have to this move. For Roadblock, if you think of this as a large search tree, it doesn't suffice to show that there's just one single path that leads to a solution, but basically you have to show that any path here in this tree always leads to player 1 winning. Now, so for vertex cover or any other problem in NP, and of course this is again talking very informally, it suffices to show one path in the search tree, whereas for a problem like Roadblock, the proof that, for example, player 1 can always win would require you to show the whole search tree and not just a single path. And that is why problems such as Roadblock are provably harder than problems in NP.